This video is on first ionization energy, which really means how much energy would be required to remove 1 mole of electrons from 1 mole of atoms. That's if we're doing math. For our purposes, you can just think of it as how easy or difficult is it to remove an electron from an atom. Okay, my AP class, we do some stuff where we quantify this and we do math with it. We're not going to do that. What I'd like you to do is be able to explain the general trends, and there are some anomalies, in both the columns and the periods or rows. I'm going to start by doing the column first. Now, if you look at, let's say, now I can pick any column. I'm going to pick the noble gases here. And what I'm going to do is I'm going to just circle them. So here's helium's ionization energy. So it takes about 2,400 kilojoules of energy to remove a mole of electrons. As I go to neon, it goes down to about maybe 2,200. Argon, 16. Krypton's below 15. Xenon's about 1,250. And radon is about 1,100. So you see this general pattern of the ionization energies decreasing as we go down a column. Make sure we're clear. These are the noble gases, and we're literally going down a column. Okay, and clearly the trend is, as we go down the column, it's taking less energy to yank an electron away. And if you're not really understanding what I mean by that, you have to realize your nucleus, which has a positive charge, right? And even if we're dealing with helium, it's got its 2 electrons here, okay, and its valence level. And if you want to rip one of these guys away, you're basically pulling a negatively charged thing away from a positively charged thing, okay? And you know, it's like pulling apart magnets. You would have to do some work to pull apart 2 magnets. Well, you'd also have to do some work to pull apart 2 things that were attracted by charges, or what they call Coulombic forces. Why is it so much difficult to remove helium, an electron from a helium atom, than it is to remove it from a xenon atom? And that's really the question you want to ask yourself, right? So as we go down the column, what's critical here is we get more energy levels. So helium has 1 PeL, and that its valence electrons are in the first one. Neon has 2 of them, argon 3, 4th, and 5th. And make sure we're clear, we're not going to be removing a core electron. We're going to be removing a valence electron, right? So if we get down to, let's say, I don't want to draw a huge diagram, so let's say we get down to argon, right, with 3 energy levels, right? Here's our nucleus for the argon, and it's got 1, 2, 3 energy levels, okay? Now, there's 2 ways of looking at this. You can look at this in terms of radius. So clearly, argon, as we go down the column, I won't even specify argon, as we go down the column, right, radius is increasing. Okay? Therefore, the electrons, and I'm specifying it should be the valence electrons, I'll put a little V next to that, right? Okay, are further from the nucleus. And therefore are easier to remove. And that means a general lower, okay, ionization energy. The other term that you might hear used, and I think I should mention this now, even though it's not really on the regions, is you can view the inner levels as acting as a shield. Okay, and what they do is they shield the valence electrons from the pull of the nucleus. Now, helium has no shielding because it has nothing between its valence electrons and its nucleus. And that's why helium has like the highest first ionization energy of any element. All right? Now, the question now, and whereas as you go down the column, you know, krypton has 3 energy levels shielding the 4th energy level from the pull of the nucleus. It gets easier to remove those electrons. Now, if we're dealing with periods or rows, there's a different pattern emerging. I'm going to work on the row containing, we're going to go from sodium to argon. Okay, so here's sodium here. Now there's some zigs and zags, and maybe in class we'd talk about some of the dips and why they're sort of like aberrations, they're sort of don't follow the pattern or the general trend. But what you should see is as you go across in a row, the amount of energy required to remove electrons always goes up. So noble gases will always have the highest ionization energy, and your alkali metals will always have the lowest. And there's sort of dips and things like that. The dips and all the reason why the pattern is not like a straightforward, looks like a smooth line, looks like it's got zigs and zags there, is because the sublevels and the specificities of electron configurations can affect the amount of energy required to remove electrons. But I'm not going to focus on those right now. What I'm going to focus on is one particular thing, and that is how the nuclear charge impacts the amount of energy required to remove an electron. The amount of energy required to remove an electron really varies based upon the radius, but also on what's called shielding. Now, shielding depends upon the number of energy levels between the nucleus and the valence electrons. What you want to recognize in a row is whether we're dealing with sodium or we're dealing with argon or chlorine or what's after sodium? Well, magnesium here. Okay, for any of these guys, basically, they have two energy levels shielding the valence electron. So the amount of shielding remains unchanged, but what you want to notice is the nuclear charge increases. Now what that means is since shieldings remain the same while the pull or the strength of the nucleus is increasing, as we go across in the row, okay, it's like the nucleus is becoming a stronger magnet. So you can think of the nucleus over here as being a weak magnet, right? And here it's much stronger. Is a much stronger pull, while the amount of energy level shielding the valence level doesn't change. So there's no change in shielding. And because of that, it becomes much more difficult to remove the electrons. And this explains the general trend. As you go across the row, it goes zoop like that. This guy up here, same shielding, okay? Or you can write same number of energy levels, right? More protons, a stronger nuclear charge. And that makes it more difficult to pull those electrons away. Whereas down here, we have the same shielding, but we have less protons. Now what I'm going to do in the next part of this short video is I'm going to talk about the trends so far and kind of try to put them together. All right, the zigzag line kind of guides us in our patterns. It's very easy to use that, okay, to visualize things. Now that doesn't mean you don't look things up in Table S, because if it's asking you to compare two things and you're not 100%, you go to Table S. It's got ionization energy, electronegativities. It doesn't have metallic activity, character, and non-metallic character. Now, the basic things we've learned so far about are atomic radius and ionization energy. What you want to recognize is this. Okay, and right, as you go down in a column, the radii get larger. Because there's more PELs, right? And you need to know the reasons. So I'm going to keep saying them, but you've got to take those in at some point and be able to write about them. Okay? Also, the larger radii tend to have the smaller or weaker nuclear charge. So, good way to remember this, as I go over to the left, now that means away from that towards that side, you get to larger radii. Now the larger radii means there's more shielding, right? Which means it's easier to remove those electrons. So atoms with large radii also tend to have low ionization energy. And this is where the most active metals were. So the general trend is wherever you have a large radii, you're going to have a lot of shielding, which means it's going to be easier to remove electrons, which means you're going to have active metals. Why active metals? Because what do metals do? Metals lose electrons. Okay? Which are the most active metals? The ones with the most shielding, so their electrons are really easy to lose. Now that doesn't mean it doesn't take energy to remove the electron. It just doesn't take a lot to remove it. It loses that electron much more readily. So when you get down to like cesium and stuff, okay, it's got a large radius. Okay? And therefore, it's got a lot of shielding. And therefore, it's easy to remove its electrons. And when it does that, it can form a cation, like metals do. And therefore, we can talk about metallic character, right? The most active metals, the metals with the most active character. What's metallic character? Losing electrons, forming cations. Who does it? Large atoms with low ionization energies. Now, notice the L's here, okay? I can't make it, right? Now, at the other side of the table, the patterns go this way, right? Now, be careful here because you've got this other column here, which is the noble gases, which throws you. So these guys, noble gases, sometimes are included in trends, sometimes not, okay? But the idea is, if you go over here, this is where you're going to have your smallest radii, okay? These guys are going to have small radii, and they're going to have the high ionization energy. Right? The highest ionization is going to be helium right here, okay? Helium's got a very small radius. It's got no shielding to speak of, right? Because it's only got one occupied energy level, right? Which means it's very difficult to remove electrons. Now be very careful because the noble gases are inert. So we can't talk about their activity. We can say it's difficult for them to, to remove an electron from one. However, if we talk about non-metallic activity, so up here we have the smallest radius. Fluorine, we need to remember, okay, is the most active metal. It has 7 valence electrons, and it becomes stable when it gains that extra electron. So it's very active, and it's got a really strong pull for that electron. So, and we'll talk about that more later. But it is the most active non-metal. So what you want to notice is the trends are basically here, right? For non-metals, the most active non-metals have the small radii, okay? And they're going to have very high ionization energy. I hope you watch this carefully and get a lot out of it.